at the Department of Physics at NYU, New York University, and also has an affiliation with the Center for Computational Astronomy at the Flatiron Institute. So Anthony is an expert very broadly in theoretical and observational cosmology. He's worked on all sorts of interesting things, such as searching for signatures of modified gravity, and also more recently, really been one of the leaders in the field of, leaders in the emerging field of intensity mapping. And as an example of this, he is the co-PI of the EXCLAIM experiment, which I'm sure we'll hear about a little bit today, as well as the science team lead. So with that, welcome, Anthony, and we look forward to your talk.
Thank you, Adrian, for that lovely introduction. So today, I'm very excited to discuss line intensity mapping. So with line intensity mapping, the hope is to use all the emission in order to find all the information in the universe, both dealing with the astrophysics of galaxies and stars, as well as even the properties of our universe. And so today, my research touches broadly into these areas, and I'm just excited to discuss these results that I've had in my research further today. So today, I'm faculty at NYU, and these are just a list of several of the collaborators, both undergraduates, graduate students, and faculty that collaborate with me. So here's just a brief outline of what I'll be discussing. So first, I'm just going to start off with the basics of line intensity mapping. What is it? What is it used for? What statistics we use? Then I'll discuss a lot of work that we're doing constructing a semi-analytic model in order to make simulations of line intensity mapping over multiple lines, something that's fairly new. And then in addition, next I'm going to talk about the EXCLAIM survey, which is mentioned I'm one of the leaders in, one of the co-authors in. And then finally, I'll move from there to work that we're doing, whereas the semi-analytic model work, its main motivation is to be used to model and constrain astrophysics of galaxies. In my talk about discussing some of the cosmological applications that we're working on. So line intensity mapping. So as astronomers, I'm sure you're all familiar with just emission, the different phases of emission throughout the history of the universe. So just going to start off with, it starts with it starts off with after the cosmic microwave background was formed 400,000 years ago. The universe, that's when the first atoms were formed, particularly hydrogen and helium, and trace amounts of some higher massive atoms. But once at this point, you have what's known as the Dark Ages, because throughout this part of history, starting 400,000 years after the Big Bang, there were no stars that were formed, and so it was just clumps of hydrogen and helium, which made up the universe. However, about 400 million years after the Big Bang, you begin to have for the first stars to form, and at this instant in time is what we call the cosmic dawn. So the cosmic dawn, you have stars, and these stars emit UV photons, and those UV photons then can reionize the surrounding medium, known as the intergalactic medium. And so at this point, then you get pockets of pockets of ionized medium, in which in these pockets expand out into where you're at the point and today where the universe is fully ionized. And so this is, but at a very low density. And so at this point, what we want to use and then at the same time, as after the first stars, you have a few generations of stars, which then have more metallicity or heavier atoms, and those stars, and then seed the chemical structure of galaxies, which then form the galaxies, the distribution of galaxies that we see today. So one thing that's interesting about star formation is that you have this downturn at low redshift. Specifically, the puzzle is sort of that not the early universe, but in earlier times, as the density of the universe of massive bodies in the universe increases, then the stars increases. But although massive halos that make up the large scale structure, although those massive halos continue to come together, you actually have lower productions of a star starting around redshift 2. And so it's not fully described why this occurs. We have ideas. We expect that interactions between generations of stars with the interstellar medium will cause star production to reduce. But this is not fully described, and more observations are needed, particularly over the whole population of stars, we think, to really understand this better. In order to do this type of analysis, what we'd want to do is to be able to measure the full gamut of galaxies, to be able to understand star formation over a large range of environments for halo masses. However, what we find is that, and so much of this work, the attempt to do this with telescopes measuring emission both in the UV and the infrared. However, particularly workhorses like the ALMA telescope really has broadened our ability to track galaxies and to be able to learn more about stellar and galactic evolution. However, with these types of telescopes where you have to detect individual galaxies, you have to identify where they're in the sky and then measure them. The problem is that you can only do this for the brightest galaxies. And so you can in fact miss a large population of galaxies because they're just not bright enough to be detected individually. So one example here is if you see this figure on the left, in this figure on the right, what you see here is that while the black dots represent all the galaxies that could exist within a field, the red dots represent the galaxies that are actually heavy enough to where they would then be bright enough to be detected. This will limit your dynamic range of what you can tell. In particular, what you often see is that many models that are built to be calibrated towards these massive bodies, but will then have differing predictions for lower mass halos, which we can't observe directly. And so the question is, even though maybe we can't individually measure these objects directly, can we statistically probe these galaxies? And so this is where intensity mapping comes in. So intensity mapping, what it does is if you look at the figure on the left, what you see is it's sort of a reproduction of different epochs of cosmic evolution. But you see these little slices here, which represent redshift slices, which could then be mapped by an intensity mapper. What that intensity mapper does is it measures the aggregate intensity in large 2D pixels and in multiple frequency bands. So you have a 2D pixel, but you measure that you would normally see on the sky, but then you measure it at different frequencies, and those end up forming what we call three-dimensional pixels, or what we call voxels for volume. And so an intensity mapper will measure the intensity in those voxels, which can then which could be correlated with large scale structure with the positions of galaxies, and we can use that and try to use that information to learn more about the underlying galaxies and by structure. And so you see here many of these applications, from the dark ages to cosmic dawn to reionization to growth of structure. Many of these types of phenomena can be probed with intensity mapping. So on the right, the figure on the right is sort of what data could look like, where you see here the little square on the left of the figure on the right is sort of what you would see on the sky, where you see these broad fluctuations because of galaxies within each of these 2D pixels. But then the right is what you would see, but then this broad sheet on the right is what you would see in frequency space. And the idea being that at different frequencies, you're measuring the emission at different redshifts, which shouldn't be correlated to each other, and that's why you have sort of this jagged pattern here along the frequency range. Then the idea is, again, you're sacrificing by having low angular resolution in order to sample at all the emission from all the galaxies to get a high sampling. And as you see in this pattern along frequency range, we don't expect correlations along the frequency bands for line intensity mapping and such. And with that, we can use Fourier transforms in order to make it separable from continuum emission, which should be correlated. So why do we want to do intensity mapping? Well, I sort of hinted at it, but again, by measuring the intensity in voxels, and correlating that with by measuring the intensity of voxels, and by performing statistics on it, you can figure out a lot about the underlying emission. For one, you can get much higher, more precise measurements potentially of star formation. You can map your ionization over, particularly over using both measurements of the 21 centimeter emission, as well as lines that appear due to star formation, which we'll discuss later. You also can measure the properties of the interstellar medium, particularly constituents of the interstellar medium will emit different lines, and so we can use, particularly by mapping multiple lines, you can try to see what regions of the interstellar medium emit which types of lines, and so you can learn more about the various environments. And then finally, because with intensity mapping, it's much cheaper, it's much faster than doing a galaxy survey where you have to pinpoint each line, and it allows you to measure emission from objects that are much fainter than what can be detected with a galaxy survey like ALMA, and so or even many of the more large scale surveys which people are familiar with, like Euclid or Vera Rubin telescope. And so the idea is that with intensity mapping, you could potentially look at probe large scale structure over much larger angular scales and across higher redshifts and scales along the line of sight. And so because of that, potentially you can, this will allow you to probe phenomena in cosmology like inflation and gravity, and possibly and other phenomena that could be limited in what you're able to do with galaxy surveys. So because we're measuring not identifying individual galaxies, you really need to measure the statistics. And so one statistic that is sort of the go-to statistic for doing intensity mapping is the power spectra. So the power spectra is just the variance of Fourier modes in an intensity map, the same type of power spectrum that you would normally see either in the CMB or in galaxy surveys. But the difference here is that the difference here is that you can try to measure this at multiple, where unlike the CMB, this is a 3 power spectrum where you see what the power is on various scales in 3 dimensions. And then the cool thing, and then also to note that these can include fluctuations both for multiple lines. And so the trick then is to try to separate those types of emissions from each other so that you can get a clear mapping to the power spectrum in real space. And then one thing that the power spectrum allows is it allows you to measure both the first and second moments of the luminosity function. The luminosity function just basically being a histogram of a histogram bending in luminosity. And so the idea is that by looking at the first and second moments of the luminosity function, these will be correlated with properties of these can be correlated with properties of the emitters, and so that's something you'd want to measure. The other type of statistic though, because those only measure the first and second moments, if you want to measure the full luminosity function, an alternative is to look at the Voxel intensity distribution. So this has been pioneered by Patrick Breese, who's a postdoc at CETA and is now at NYU. And so the idea is that you can make a histogram of the intensities, and it serves as a 1-point function that is insensitive to the full luminosity distribution, the luminosity function. And so the idea is that this Voxel intensity distribution, or VID, is then can be correlated with properties of gas and the distribution of the emitters. And so one thing you can see on this figure here, if you look at the figure at the bottom, what it shows is that you have a sort of the error in the luminosity function on the y-axis, and on the x-axis you have luminosity. And what you see is that if you have both the power spectrum and the luminosity function, which is the relative, respectively, the blue line and the blue curve and the red curve, if you put the information from both of those statistics together, you can actually get even lower errors than you can independently. And so this is forecast that was done for a COMAP-like survey, which COMAP is right now, that's the detector that's running, the telescope that's running right now to measure emission from CO, from carbon monoxide. And so, but anyway, this is, shows the power of using both statistics together, and in particular, you can sort of think of the VID sort of as constraining astrophysics to then allow you to have to make better constraints of cosmology using power spectrum. That's one way to think of it as well. So that's the basic primer. Any questions? Okay, all right, then I'll move on. So so with that primer, now we want to get into multi-line IM models and how we're doing the work in order to make that possibility of analysis for multiple lines of reality. So one thing is that we're now in a stage where over the past 15 years, there's been much work into making into proposing various experiments that will be able to various telescopes that will be able to measure multiple lines of emission over multiple redshifts ranges and angular ranges. And so much work has been done. It first started with the 21 centimeter cross correlation detection using the Green Bank telescope in 2008 by Zuchi Cheng. And so, but much work has been done in order various methods, both repurposing previous telescopes to use for this effort, as well as writing proposals and winning grants in order to make new telescopes. And so much work has been done looking at multiple different types of lines. You can see the figure here, but there's much work to be done. Of course, people here represent both Hera, Chime, as well, and so there's I think some CCAT people here as well, and so there's much work to be done, and there's a whole community that we've been working together in order to move this effort forward. So the lines are looking at multiple types of emission, and the thing is if you're using multiple lines, allows you to probe different environments, have different advantages. So for example, you have the 21 centimeter emission, which traces both H1 neutral hydrogen in the IgM, as well as during reionization, and the dark ages, and it's also present in, in galaxies post reionization. So throughout cosmic history, 21 centimeters is a very viable candidate for that. Carbon monoxide, it's known to trace. It's a very bright line, traces H2 gas within the interstellar medium, and so it's known to you want to use it to trace the molecular gas regions inside galaxies, and so it's typically traces the cold regions, whereas C2 on the other hand, it normally traces the ionized regions within the ISM, and it also probes the star formation rate. And then another line that also I've been interested in the past is LIM alpha. LIM alpha, what it's great for is it traces star formation and H1 in the IgM. And so particularly if you want to trace more about the IgM, which having cross-correlating H1 and LIM alpha would be a really significant probe of that. So notice on the bottom, it sort of shows where the different lines are located on a typical spherical spectrum for a star-forming galaxy. Okay, so one line that I've been interested in, I've done much work in, is C2, ionized carbon. And one thing that we were interested in, in 2012, one of my projects as a postdoc was looking at CO, and we made this, we made a constraint, but we also predicted that that Planck, which was just starting to get the first sets of data sets at the time, was able to, we thought that Planck would be able to, if you cross-correlated Planck with Bose quasars, you could possibly detect C2. And so a few years ago, we were able to actually do this. What we found was that what we tried to do was, we knew that Planck, although at the frequencies that we're looking at, for frequencies greater than 300 gigahertz or so, We knew that it would mainly be dominated by dust emission from the Milky Way galaxy, as well as what is known as the cosmic infrared background, which is continuum emission from dusty stars outside that's an extragalactic source. We knew that, but also to those frequencies, we would expect that there should be some emission from C2. And so what we did was, in order to tease out the C2 emissions, we cross-correlated quasars, redshifts 2 to 3 from BOSS, with these maps, Planck maps. And the idea being that these quasars should only be correlated with large-scale structure, which should be correlated with just the CIB emission and any C2 emission. And so what we found, and then what we did was we actually marginalized over the CIB using a model to then try to see if there was any excess emission that would be consistent with C2. And what we found was we did find an excess emission greater than 3 sigma. And so we were excited about that. However, and so what we find is that the measurements that we found were consistent with C2 models in the literature, although right now we do feel like those models are a little bit unrealistic because they predict too much star formation at low redshifts where we were looking at. And so only thing we're not sure, we still, obviously the excess is still there. We did various checks to make sure it was real. But as far as modeling what the emission is, we're not fully confident yet that it's totally C2. So it's still a mystery. However, we have plans for EXCLAIM will be in a survey with which we should be able to do a better job of removing any kind of continuum emission from like the CIB, for example, in order to be able to get a better constraint on C2. And so that's something we're looking forward to in the future. Okay, so one also issue that we've been doing a lot of work on lately is trying to create better models for intensity mapping. So we have these various lines that we're looking at, 21 centimeter CO, C2, Lyman alpha, but many of these lines, many of these line emission models, when you try to, if you want to try to take this, if you want to try to take these lines and then be able to do inference with them, we're going to want to be able to, sorry, I see a question. Okay, I can see a question in the chat. Why redshift 2.6? Specifically, why we chose that was because the range of quasars that were available from BOSS that we used at the time was from redshifts 2 to 3, and which matched, and it matched with the frequencies of Planck. So for Planck, it's C2 there are 3 frequencies that we looked at, and the middle one was at 545 gigahertz, which matched with C2 at redshift 2.5. And so that's why we wanted to pick that one. But we didn't want to, but the key thing is, in order to remove CIB, we needed other bands that we expected wouldn't have C2 at that redshift range, in order to then model just the CIB to then use that for the C2. Now, of course, we didn't do that independently. We made a joint fit that it just put all the data in to be able to do that analysis, but that's why we picked that redshift. Hopefully that was helpful.
Yeah, but I'm just wondering, in your last slide, there was also N2, but so I don't know anything about this field, but could you not check with N2, or I guess that's not part of the range that's available, is that it?
So one thing with C2 is that it was useful in that it, thanks for the question, Victoria. So one thing that we checked was that with C2 is it's like the brightest line in the SED, and so there were other lines that were available, but those are subdominant. And the big part of using C2 is that we could be confident that looking at the expected line ratios, that the signal that we should get shouldn't be from other lines. And so really it only allows, because the C2 was so much brighter than all the other lines combined, we were able to ascribe that to C2, but we wouldn't really be able to do it with any of these other lines in that range, because then C2 would be sort of a contaminant for those, if that makes sense.
Yeah, okay, thank you.
Okay, so anyway, so we want to make better models, because most of these models, many of them are made using just sort of arguments for star formation, but really, well, arguments, empirical models, but many of these don't capture the full interactions between stars and the environment, and the gaseous environments that then affect the galaxy evolution. And so we wanted to do, and so the other side of it is to try to do simulations. But the problem with simulations is, for simulations like Illustrious, for example, you would get like one simulation per year. And so this is not really useful if you want to do if you want to eventually do type of multiple. If you want to use multiple simulations, you want to do simulations for multiple environments. Plus, with simulations, oftentimes you still have to have models that describe the physics, sort of in very low resolution, on scales that are much smaller than sort of the grid sizes that the simulations can probe, and this is known as subgrid modeling. And so there's sort of an in-between method is known as semi-analytic modeling, where basically you can take an embodied simulation and then paint sort of star formation and galaxy models on evolution models onto these dark matter halos. And then the key thing is that you can actually simulate what the given a halo, what the star formation, you can actually make models that are calibrated to data that tell you what the star formation should be for a particular massive halo, how many galaxies should be formed, how those galaxies should evolve. And so if you allow that to be those to be calibrated to data, then it allows you to basically make something like a simulation to be able to, and it's better informed than semi-analytic models in particular, because it allows for scatter, it allows for effects that it allows you not to just say each galaxy of a particular mass can have a particular luminosity. It allows you to really capture the effects of the environments that are present for each individual galaxy, and so it allows you to have better approximation to an actual simulation. So a lot of this work is work I've been done with that has been done by Shengxi Yang. Shengxi Yang was also the one who led the measure. Is a grad student of mine who's currently on the market. She's the one who also led the analysis for the C2 excess detection. And so here, one thing we were working on is we actually use what we want to do is construct maps of line intensity mapping for various lines, and then use those to make models of the expected line emission given these maps. And so we were able to do this. We were given this semi-analytic model. And so first, one thing we had to do is check that the SAM was well calibrated. And so here, what you see is the luminosity at various redshifts that are labeled here, as well as we looked at lines. Here they show examples of lines C2 and this carbon monoxide line for the transition J = 3 to 2 line. And so here, and this is fit with some ALMA data, some IRM data. And what you see here is that you have pretty good fits. You do see in box number 2 on the top right, there is some variation here, but for the most part, you do see pretty good matches. One thing to note, of course, is that we're really matching this all on the sort of the large star formation end, because these are the galaxies that are going to have high UV, so that you can be able to detect it. But notice that we're not having any data from sort of lower star formation galaxies, and so that's what the intention of the SAM is to model, is to get back to that initial goal, to be able to model the physics from low mass and low star formation halos. And so we were able to use this. Once we were able to have our halos, we were able to make mock maps of large line intensity mapping. So here we show. So we did this for several lines, for C2, particularly C2, CO, and C1. And so you can see various maps here, sort of in the format where you can see this one patch on the sky versus a 2-degree patch on the sky versus versus the variation along the frequency range. And so these were simulated, particularly this C2 one was particularly simulated for the EXCLAIM survey, which I'm going to talk about later. This was only done for a small patch for 2 square degrees in the sky, because that's the size that we were able to simulate consistently, given the 400 gigaparsec cubed boxes that were available to us for the in-body simulation. However, we do expect that this could be expanded out. That there are ways to possibly expand this out to larger areas, which I will get into later on. But so anyways, and then we also have models for the CIB, for foregrounds like the Milky Way. And so we were able to make these mocks. And then in addition, we were able to use the results from the SAM to be able to then simulate star formation rate mass relations. Particularly, these are we were able to make these simulations and then compare them to other empirical models. And so we do see a significant difference. Particularly, we see differences in the star formation mass relations, which is this top plot here, particularly in the high mass range for could just possibly due to different quenching models, And then we see in the bottom plot here, the luminosity mass relation. We see a difference due to different predictions for the stellar feedback. And so the thing here is that you can imagine, you can see that these models do, these models do match for, and so while these models do match for at some ranges of masses, they differ in other ranges of masses. And so the hope is to be able to use data to eventually be able to discriminate between these models. And so in particular, what we were able to find was that if you plot statistics for these, like the 1-point PDF or the Voxel intensity distribution, which is shown on the top, and then the power spectrum, which is shown on the bottom here for various lines. So both of these are comparing models, the SAM model of CO, which is the red curve, with other models of CO, like this blue curve here, which is the CO 1 to 0 model. That's from Tony Lee et al. So what we see is that in the same for the power spectrum, what you see is that there is a difference. And if you actually do a chi-square test with these two models, you can show that a survey like CO map would be able to discriminate between the two. And so this is very and so this is hopeful that as more of these surveys come online, not only will we be able to detect emission, but hopefully we'll be able to actually do some science with them. We'd actually be able to pull that back and to see which models of CO are more likely, and then possibly be able to make constraints. So that was that paper. Much work is being planned for the future. For one, we want to actually make empirical models that we can describe based on the SAMs. One major reason we want to use that is to be able to, for the only two things. One, we hope to be able to, that's one thing we're working on now. And then in addition, one thing we want to test is for these different statistics, could you reproduce them by just assuming a distribution of halos and assigning some kind of scatter to an empirical model, and would you be able to then reproduce the full results of the SAM, at least for the various statistics that we're interested in. So this is not a foregone conclusion. You would expect it would probably be true. If it is true, then that would actually open a window to be able to make rapid simulations, because then you could just be able to simulate more survey-sized areas of the sky quickly. So that's one area. If the avenue cuts off, if there are extra effects in the statistics that can't be fully described by, for example, just a clustering model, like the halo model, for example, and an empirical luminosity mass relation, then what you may have to do is you may have to use topics like machine learning to be able to make larger simulations. And so that's something we're also thinking about. We also want to be able to model cross-correlation statistics and be able to match those better with properties of galaxies. And then finally, we want to be able to construct a procedure for actually being able to go from the SAMs to parameter constraints. And that's something that we're also considering as well. So now I want to talk about the EXCLAIM survey. So the EXCLAIM survey is a consortium of our 9 institutions, in which are led by Goddard Space Flight Center, in particular the PI being Eric Switzer at Goddard. EXCLAIM, it's constructed as a CO and C2 mapper. EXCLAIM stands for the Experiment for Cryogenic Large Aperture Intensity Mapping. And its goal is to be able to, it has a few goals. One, be able to find what factors actually led to this downturn of star formation at redshifts less than 2. To see more about to discover more about the abundance and excitation of molecular gas, by observing both CO and C2 lines, being able to use we want to use CO in order to trace molecular hydrogen in galaxies, and then finally we want to be able to use intensity, and by being able to measure these different lines, we can then have a better idea if these lines at higher redshifts could be used. Then what we're going to sample could be at high redshifts, we could be used to do cosmology over very large scales. So the various science goals that are so those are the various science goals, and so in order to do that, we're going to cross-correlate maps of CO and C2 that EXCLAIM is going to create with galaxies and quasars from at least from the BOSS survey, but we'll be updating those with galaxies from quasars from EBOSS. With EBOSS, you'd be able to, particularly with quasars, EBOSS would allow you to be able to get quasars from lower redshifts than what you can with vanilla BOSS. And then also we'd be, and so with this, it should, from these two plots here, what it shows is that with these black bars representing the error from EXCLAIM, with these cross correlations with EXCLAIM, and these are for various lines being cross-correlated with particular galaxy samples, we see that particularly with many of these, we'd be able to tell the difference between different models, which are with the different models represented by different these different symbols here for each row. And then here at the bottom is so the top is the constraint for CO, their various CO lines, carbon monoxide, whereas the bottom is the predicted constraints from C2. So this is going to be a 400 square degrees extragalactic survey and a 90 square degree galactic survey. The point of the galactic survey is to be able to map both C1 and C1 being, as well as H2, with C1 being a tracer of H2. And then the idea is that we can use all that information together to get a better handle on what the CO to H2 ratio is. And so we can use that to then infer what how much H2 are in the extragalactic regions, where in those cases CO is the ideal tracer for H2 because it has a permanent dipole. Unlike H2, it has a permanent dipole, which allows it to be detected more, the emission from that to be detected easily. So we expect the original idea was that the first engineering flight would take place in 2021. We expect that it's probably not going to actually take place then due to delays from COVID. So it's probably more like 2022 for the first engineering flight, and then the first science flight a year after that. And so it's going to be really exciting when we can get that data and start to hopefully detect, and then we expect to be able to detect C2 with very high significance on order of 30, 10 to 30 signal to noise, and CO we expect to be able to detect with at least a signal to noise of 8. So I'm just going to skip over these parts, talking about sort of the cryogenics of the survey as well as the high altitude of the survey at 36 kilometers. The high altitude is what allows it to be able to peak between atmospheric lines to be able to get the galactic and extragalactic signal. Also, another so that's talk for EXCLAIM. Another survey that I'm also involved with is SPHEREx, particularly through the Center for Computational Astrophysics at Flatiron Institute in New York City. And so basically, one thing I'm very interested in is the intensity mapping signal. And so one project that I plan to do is to be able to actually use the same to model the cross correlations between SPHEREx and overlapping surveys, including possibly the SPHEREx survey itself with the galactic sample, but also with other surveys like Euclid and DESI. And so the goal being that is to then, and then to be able to relate that to observables, and then be able to relate that signal to observables like the ISM and intergalactic physics as well, intergalactic medium physics as well. So finally, so those are sort of the astrophysics applications for this, but we want to talk. I want to conclude by talking more about some of the cosmological applications I've been thinking about. So one of the things that I thought about is doing Fourier analysis on the sky. So particularly, and this is work this is work inspired by Adrian's work for 21 centimeter. So the idea being that if you wanted to analyze this, although for small areas you can expect to treat, you can sort of think of it the coordinates, the natural coordinates of frequency and angles as a 3D box, but in reality, because you have multiple lines of sight that differ as you look at different patches of sky, you'd actually expect the spherical coordinates to be the more natural coordinate system. And so for that, if you want to actually use that basis and not lose any information, you really want to be able to have a harmonic coordinate system that fits with that. And so spherical Fourier-Bessel analysis is a way to do that. In particular, what we this is made, slightly differs from Adrian's formalism in that this is made to be ideal for a shell for a shell volume instead of a spherical volume, and in particular, and so this is parameterized by moments L, M, and N, where L and M are sort of your harmonic angular coordinates that if you've done C&B analysis, you're familiar with, but also the other third coordinates would be along the line of sight. Is this coordinate N, where it labels different different angular scales that different Fourier modes that can be sampled in a finite volume like a shell, like a spherical shell. And so what's done is we use a coordinate system where we pick the K's such that the function that's being described goes to 0 both at the inner and outer boundaries of the shell. Sort of like what you would do for an FFT, but except for a spherical shell. And what we see here, and what we were interested in is would this make, we were interested generally in would this make a difference in cosmological analyses. And one thing that we were interested in is weak lensing as a test case for this. Specifically with weak lensing, it's something that's been thought of a lot for intensity mapping. In particular, you have, unlike the C&B gravitational lensing of light rays, you have multiple source planes, and you don't have self damping at small scales. And so it would be very, and so you could potentially get a lot more information about the large scale structure along the line of sight as it's lensing intensity mapping. And so here, what we find is that while this has normally been done assuming that all your intensity grid is in a box, what we wanted to do is we wanted to consider what would it be like if the grid was in a spherical shell, and would that affect the statistics? And what we found is that it should. Specifically, what we would do is we model how the correlations between different Fourier modes of the intensity map are correlated with each other due to lensing, which they're uncorrelated, but lensing correlates them. And when we were able to use that to build an estimator for what's known as the lensing potential, which describes how light rays are lensed along the line of sight, assuming the Born approximation. And what we find is that we found an estimator for this lensing potential, as well as what the noise would be, which is shown here. And we actually forecast this for the HYRAX survey. And what we find is that if you compare estimators that we used before, where you assume that the grid was just a box, versus this shell, you actually do get a deviation at large angular scales, or a small L. And so it actually can affect to a degree what how much information you get out of it. And so we expect that this could improve growth on large scales. Next steps, we want to improve this estimator, because previously we used an approximate form of this harmonic space, but now we want to use an exact form where we're actually, and so unfortunately I don't have time to get really into it, but it's just, we are proving constraints on this, and we're also considering what happens with nonlinear effects as well and how that affects this signal. And so that's work we're concurrently working on. One thing we're also, and it says, and then one other thing we're also working on is for inflation constraints from intensity mapping. So in particular, we expect that basically the clustering bias, or which describes basically how the galaxies that can emit, for example, 21 centimeter or CO or C2, those galaxies tend to live in high density regions. And B is, which is the bias, describes how those different galaxies cluster in dark matter regions. And so specifically, we expect that because in normal in sort of vanilla inflation models, like inflation where you only where it's only sourced by one field, you would expect that field to be non-Gaussian. I mean, you expect it to be a Gaussian field for the most part. However, for inflation, if you have multiple fields, or if you have alternatives to inflation, that can be deviated in such that you can cause large scales and small scales to be correlated, which then leads to a non-Gaussian, which then basically leads to the non-Gaussianity can lead to large and small scales being correlated, and so that can actually affect the clustering bias of the emitters. And so, in particular, what we expect is that you would see a shift in the bias that scales as 1 over k squared. So you would see the effect on very large scales, or small k, and it will be scaled, and it will be modulated with this parameter FNL, which describes the which can be correlated with whatever inflation model is true. And so people want to measure this FNL parameter in both in CMB as well as Galaxy surveys, but Galaxy surveys in particular can extend this, have a better chance than CMB to be able to extend this down to constraints of FNL less than 1 due to being able to sample large volumes. And then intensity mapping, since it can sample even larger volumes and potentially than intensity mapping, it could possibly do an even better job. Now, of course, since this is a large scale effect, you have to be careful about, Adrian will of course tell you that you have to be careful about contamination on large scales. And so one possible way around that is to consider, instead of considering using 21 centimeter for this type of measurement, to use maps of CO and C2, which are expected to have much smaller foreground contaminations than you expect for 21 centimeter. And so people have there have been some work done on this, but one thing we wanted to look at, and people have predicted that you could, with surveys sort of in the next 10 years, we should be able to get competitive constraints on FNL. And of course that would only improve as our sensitivity gets better and be able to map larger volumes. But one thing we wanted to look at, a student of mine looked at, is how this is to be affected by interlopers, or lines that would contaminate the line that you're trying to use to map. And what we basically find is that they can affect things a lot. For example, if you try to use C2 to constrain non-Gaussianity, but it was contaminated by low redshift CO, it could be a severe contaminant for this. However, if you were able to, you can potentially use cross correlations to try to separate out those two signals in order to get a good signal. And that's what's represented sort of by these yellow ellipses are the errors. Particularly FNL is shown here along this column. And so, well, with the error being here, whereas this yellow curve is what happens to the error if you have large contamination. Whereas if you're able to use these cross correlations, it doesn't remove the contamination entirely, but it limits it to a large degree to where you're able to get sensitive measurements again. And then lastly, one thing that we're looking at as well is lensing, using cross-correlating lensing with line intensity mapping. So this is not obvious how to, so in particular with the CMB lensing field and the line intensity mapping lensing, you could use either these cross-correlated with galaxies in order to constrain FNL potentially. So the top figure is was a prediction for C&B lensing cross-correlated with galaxies, and how that could from Desi and Sloan, and how that could affect the constraints on FNL. And what you find is that particularly when you add lensing, it reduces the error from these dashed lines to these solid lines, and so that's pretty cool. And also, a lot of it depends on how correlated the CMB lensing signal is to the galaxies. But we expect, particularly as you use more galaxies, they'll tend to be more correlated with the lensing field. So one thing we want to do is we're trying to predict this for, but not only other surveys like SPHEREx, for example, but we also want to look at how this will be affected if you replace the CMB lensing with line intensity mapping lensing surveys. And so those goals are something that we want to do, that we're working on currently. A student of mine is working on currently. And so hopefully with that, we'll be able to just expand what we can do with inflation physics with these types of studies. So in conclusion, line intensity mapping, hopefully I've convinced you that it's uniquely positioned to answer questions about galaxies, star formation, and cosmology. Really, we want to stress the idea of doing a multi-line campaign. Multi-line, by multi-line meaning multiple line emissions. So the SAM is this first simulation. Is the first simulation over sort of a large area that's able to really map multiple. The first simulatic model that's able to map multiple lines. So there's several of these models of these simulations in the literature where they just map one or two lines to CO or just C2 over large scales. This is the first one that's able to do that. This is at least one of the first ones one of the first couple that I know of that's able to do this over multiple lines. And so, and with this, we can, particularly by having multiple lines, you're able to see how different parts of galaxies that are traced by different lines are then related to each other. And so that's something that we're discovering more and more using that we're pursuing more and more with these models. We want to construct a realistic, and so we've constructed realistic models, LIM mocks, and so we're going to be using these further in order to see if we can make surveys over large areas we can use directly with different surveys like EXCLAIM, like SPHEREx, but also to be able to then backtrack into being able to aid in parameter constraints. EXCLAIM, really excited about that, to be able to map CO and C2 definitively with very high spectral resolution. And that's going to be used in order to learn more about star formation in ISM. And then with lensing and cross correlations, we open many opportunities for cosmology with inflation, as well as being able to, with lensing in particular, being able to trace growth of structure and gravity. So thank you for your attention, and be delighted to answer any questions.
Okay, thanks very much, Anthony. That was great. So we have time for questions. So feel free to raise your hand in the Zoom menu and I will call on you. I know Adrian and I both have a few, but I can open it up to the floor first, more broadly.
Okay, so Adrian, you have a question? Oh, I see questions from Adrian and Juno. I guess Adrian go first, and then Juno, I guess.
Sure. Thanks for the talk. As always, super interesting. I have 3 questions, but I'll ask just one for now. So for the results on the non-Gaussianity, when you showed how having the CO lines help you basically, cross-correlate to high Z CO lines, helps you do better. When you were considering the interlopers, does that already incorporate the kind of the redshift space distortion, degeneracy breaking? And so this is above and beyond that, is that correct?
That's right, yeah. This always assumes RSD. The thing is RSD, it's the effect that have on the power spectrum is limited because you have this sort of beta and beta squared term that's predicted with the Kaiser effect. And so which we also include the fingers of God, but mainly it's in the Kaiser effect that you see this sort of extra distortion due to interlopers that doesn't match with the RSD effect. So, yeah.
Great, thanks.
I seem to have a lot. So maybe Jordan, I should let you moderate.
Okay, yeah, I can moderate her. Juno, if you still have a question, you're welcome to unmute yourself. Noticed your hand go down. Otherwise, maybe if your question's been answered already, Mohit, let's go to you.
Sure, Anthony, it's a great talk. Thanks a lot. So I have a question. I have two questions, but I think I can also wait for the second question if we have time at the end. Or I can just ask, or you can select any one of the two. So the first thing is, I know there is a C2 star formation rate relation, but if I'm not wrong, so there are many contributors to that, different contributors of the, I think, components of the ISM that contributes to that, the C2 intensity, which includes, like, I think, H2 gas and ionized gas, as you have already said in the talk. So I'm just wondering if, what is the current status of the calibration of that CO star formation relation? And in your talk, you talk about multi-line follow-up plans. So is it possible to untangle the contributions from different, from those different ISM components so that we can actually map, for example, cold CO gas or cold H2 gas in the ISM of different galaxies? And second question is, I understand that for the local universe, CO line is basically falls in the FIR band. So are there any upcoming missions that we can use to map the C2 lines in our local universe? That's all. Thank you.
Yeah, so it's a good question. So I'd imagine for, I think the second question might be easier. So so C2 is at 1.9 terahertz. So you would need a survey that would extend basically well past Planck. So you're well, 150, yeah, so it's around 160 microns. So I expect with I guess Herschel might be able to do this, but I'm not aware of any surveys at the moment that are actually planning on doing C2 in a local universe. Although that's something that, because most of the surveys you see with ALMA, for example, they're looking at it more like at redshift 2 or so. So yeah, that's something that I'm not sure aware of. I think it's possible Herschel might be able to do it. As far as, but I'm not aware of anything coming online recently. So as far as your other questions, I would expect that, I'm probably going backwards. So so as far as being able to separate out this, well, for one, the C2, the status of that, yes, C2 is something that we expect to be able to measure, we'll expect to be present both in the IGM. What's the latest status of that? We are starting to see models of that being, empirical models of that being formed. The SAM that we make is mainly focused on the Galaxy emission, not the IGM, although it's something that we could, so the SAM doesn't predict what the IGM is, although we could include those models as a simulation on top of the SAM. And so and so that would be affected by whatever the UV star formation is that's predicted by the SAM, then affecting whatever the surrounding galactic medium is, intergalactic medium, to be able to predict the C2. And so we expect that's something that could be done, but that's not anything that we're currently working on. In particular, if we were able to make that kind of joint simulation, then we would expect to be able to possibly use, I'd imagine possibly at high redshifts being able to cross-correlate with neutral hydrogen from 21 centimeter, or 21 centimeter from neutral hydrogen, to be able to then identify to then be able to sort of identify the neutral regions and in turn identify the ionized regions. Also, too, cross correlations with C2 and with also cross correlations with CO could also possibly do that as well at high redshifts in order to be if depending on how much CO there actually is at high redshifts, which is very uncertain right now. But depending on how much of those lines there are, how much of the line intensity there are, you could possibly be able to discover that, but that's not something that's been worked out.
Okay. Thanks. It's very
Thank you
interesting.
very much.
So I'm going to ask a question before I turn it back to Adrian, because I know he has more. And maybe this is antithetical to line intensity mapping, but there's a lot of interesting information in the continuum as well. So like carbon-2 is sitting on top of the dust continuum. And so for SPHEREx, these lines are on the optical or sometimes UV continuum. I'm wondering if there are tricks one can play to get at this sort of information.
Yes. So one thing we have also thought of wanting to discover more, because we are simulating CIB with the goal of being able to actually, because there's much information about star formation in the CIB itself. One thing we even tested is like, if you have CIB, could you then improve that information by using C2, for example, having a joint constraint with C2 and CIB for like a model of star formation in the galaxy. And what we find, at least simply, is that on preliminary check that I did finds that you should be able to improve those constraints from CIB alone at about potentially a 30% level. So that could be something that could be useful. So then the question, so then what you could do is that could be helpful. That could be helped by, and so that was a case where you had CIB and C2 both cross-correlated independently with galaxies. Potentially, you could cross-correlate those signals together. It's a different kind of system because you have a 3D map for C2 and it's suited a 2D map for CIB, but you can build estimators that handle that. Just like you can with this lensing in a 3D signal as well too. So, so that's something that could work. That I believe would be a likely possibility.
Okay, very cool. Adrian, do you want to ask another question?
Sure. So just quickly with the some of the earlier slides you showed, where you showed the being able to combine the voxel intensity distribution with the power spectrum to do better. Does that rely on having multiple lines to cross-correlate to help remove the foregrounds in the voxel intensity distribution, or no?
So I think this relies on I think this relies on the perfect case where you don't have where the foregrounds are taken care of somehow. So so yeah, you could but if you do one thing that's being that Patrick Breesy has also introduced is this idea of a what's called a conditional voxel intensity distribution. And the way that works is that basically you compare the voxel intensity distribution to the one where you have where you make each voxel condition, it enters into the histogram conditional on if it has a bright galaxy. And if you do that and you play, and it's based on tricks with Fourier transforms and Parseval's theorem, but basically what you find out is that you can use that to actually remove at least in these simulations that you're able to make, he's able to remove the effect of foregrounds from the voxel intensity distribution. And so because you'd expect normally, otherwise you would expect basically you would expect the foregrounds to basically just shift the voxel intensity distribution. So, but by being able to do this kind of trick, he's able to remove that effect. And so you have that. And so it's supposed to be like the voxel intensity distribution analog to a cross-power spectrum. And so, which also is supposed to remove any bias from foregrounds. at least from common foregrounds. So, sorry, from uncommon foregrounds. So, yeah, so that's so I think with that, I would expect these to not be affected somewhat by that, but if you were to use cross-power and this conditional PDF, I'd expect that you wouldn't get much worse than this. But it's not something that, but it's something that he's still working on. He's as far as how to as far as how to simulate that to more realistic intensity models, and so it's still a work in progress.
Thanks.
All right. Adrian, do you have one last quick question? Or if not, we should, I think, start to bring things to a close.
Oh, it's getting late. Let's close it up because we've got the grad student meeting coming up soon, and then we'll be in touch. It's easy enough for us to talk.
See you virtually at a conference at some point.
Yeah.
Okay. Well, perfect. Well, thanks for a great talk, Anthony. That was super interesting, and we welcome everyone to join me in thanking Anthony for visiting us virtually today.
Thanks for having me. Enjoy it.
Thank you very much.